Is a man that he didn't know I knew him for so many years because his book was the first book we used in grad school, Dr. David Kuck, and I won't say anymore. Next to him is a woman who loves Intel because they allow her to, understand or to be surprised. And this is Dr. Genevieve.
Was the surprise by used?
She doesn't treat me with a whole lot of respect. If you don't know that now, you will know it by the end of the presentation. Senior fellow Tom Piazza, he's he does the Gen graphics. He's been the Gen. Oops, sorry. Yeah, that's the danger of these mics. Next to him is Ajay Bhatt. If you all remember the commercial on the Intel Rockstar, there's the man. Kelin Kuhn. Yeah, everybody, let's clap for Ajay. We all make fun of them because we're actually jealous they didn't pick us and they chose him instead. Kelin Kuhn. Kelin is Dr. Kelin Kuhn. She's a researcher. Are you an LTD?
I'm an LTD.
Okay. And she does every process and transistor question that you have, Kelin will be the one to answer because she's the one that develops those and gets them ready for product. And then Dr. Knut Grimsrud. DeLorean expert as well as storage expert here at Intel. So,
you need your car worked on? Come your back.
That's right.
DeLorean questions, storage questions.
They're both the same.
Just keep his car very empty.
Okay, so
according to Intel's optimization manual, the L1 data cache consists of 8 banks, and I'd like to know if each of those banks in the L1 data cache have a separate read port and write port, or do they have a single combined read-write port?
I can tell you the associativity algorithm and everything else, but the read and write ports, you didn't answer that question? No. We're stopped. You get a card. I can't tell you. My guess is there's separate read-write, but I don't know.
Do you see any major overhauls in computer architecture happening sometime in the coming decade? And if so, what will that likely entail?
Boy, is everybody looking at me. How about you, David?
Yes, it is. But lots of people are off measuring lots of things to try to address that, but I can't speak in any official way about what's going to happen.
Yeah. I don't know if you came to the talk that I did yesterday. We're spending a lot of time, as with other companies in the industry, looking at the exascale challenge and how we're going to deliver machines that at 10 to 18 operations per second. And the target we've been given for power is 20 megawatts, which is an order of magnitude less than where they would be if we just continue down the standard progression. What that means is the programming models are going to have to change, the underlying architecture is going to have to change, the memory, the fabric, and everything else. And that's why the R&D investment is going to be on the order of billions of dollars by the industry and government. So will it change? Yeah. Do we know what it looks like yet? No, there's a lot of research that's going to go on. You want to come up and get your card? I do need the exercise.
Yeah, hello. There's quite a bit about Thunderbolt at the conference, and I just attended a couple sessions, and it looks really cool. But it's basically a high-speed wired dock. And I guess the question comes, well, why not go wireless? And so I would appreciate comments on using wireless docking versus a wired dock like Thunderbolt.
That's an interesting question. There are hope, as we go towards ultrabook kind of form factors, placing connectors is really an issue. Right? There's not even a place to put even a docking connector. So there are a whole bunch of use cases where wireless would make sense. But then there is the issue of display. And when you have very high frame rate application, then you do need wires. I think what Thunderbolt allows you to do is it says two protocols. For those of you who don't know about Thunderbolt, it supports two protocols. One is the display port, another one is PCI Express. And it allows you, from single connector, it allows you to do both these, support both these use cases. Once you have PCI Express, you can convert that to any legacy protocol if you want to, and you can create a dock. People are trying wireless docks, but wireless will have to become a lot more reliable. I mean, it works for a lot of LAN applications, and you can do USB over IP and some of the other things, but I think the usage is limited. It will get interesting when we go to 60 gigahertz kind of radios, where we'll get more bandwidth. And
at limited range.
Big one?
At limited range. You know,
and within the range. I mean, when you talk about docking station, I'm assuming that it is mainly proximity-based use case.
Today's keynote, there was a presentation before. Intel is hardware heavy, chip heavy, but from now on, it moves to the user experience heavy. The triangle is reversed. But first, today's panel is mostly hardware dependent. So, do you think is it get much further than change, or do you need some restructuring of this structuring?
I'm sorry, I don't. Is the question about user experience and Intel going to change its design practices, or what?
Right. Today's keynote, previously the Intel is the hardware design heavy. The trial was based on the hardware and the experience is on the top. But today, the keynote says that it will be diverse and it focuses on the user experience, and the hierarchy is reversed. But today's presenter is mostly hardware. So do you think it still works, or do you need some restructuring or some changes required?
We're not going to restructure you, Steve. It will be okay.
Yes. No respect.
There was no respect. I think, one of the really interesting things about Lizz's keynote this morning is not just suggesting that we need to have a restructuring, but it's also about what's the process by which we drive innovation. And for Mooley, and indeed in Paul's keynote yesterday, and I think running through a number of our businesses, is a much stronger sense that it can't just be about solving technical problems. It also has to be about having an incredibly strong sense about what it is that makes technology compelling, what's the experience we want to deliver, what are the kind of usages we want to enable. And I think you see a whole range of consequences of that kind of thinking happening at Intel. Whether it's the appearance of user experience groups in all of the businesses, whether it's the fact that we have a lab now in Intel Labs dedicated to those questions. I think we're moving through that process of both bringing new people into the company who have that skill set, and then also re-educating my peers so they can also help drive this effectively. We'll re-educate you first.
That's excellent. Excellent answer.
There was a lot of interesting things about the Xeon 5600, which I think is the next generation, in terms of its enormous power, orders, etc. I'm curious as to what degree servers built around that will overtake or catch up to and overtake what is considered a mainframe today, and if the pace there isn't faster than in mainframe technology, and to what degree does that impinge there? There's a second question which may come in from a different angle. It was mentioned that a version could be brought out, wasn't announced, but could be brought out for massively parallel machines, which would sort of strip some stuff off but still be software compatible. Is that sort of going back to what Intel was doing 20 years ago in the massively parallel machines?
Wow. So first question.
Just assume what I said was true. You don't have to.
Okay. So the first question. You probably, in fact, you may have been the person that asked the same question a couple of years ago. Xeon is getting more and more capabilities, and it overtake mission critical on the high-end risk. It is moving into that market segment, but like with mainframe, there are other aspects of mainframe that you get in terms of 5.9 reliability and things of that nature that people are still willing to they want to make one phone call and they want to have that one system and they want the hardware and software to be reliable and they've written their code for years. I mean, the credit card guys tell me that the worst thing they need to have happen is their system go down on December 3rd or December 24th at 6 p.m. when everybody's making their last second purchase. I think mainframe is a class. We think of mainframe as a box. I think the class of mainframe type workloads are actually becoming a critical part of what we define as the cloud. And the whole distributed database architecture, when you look at how that architecture is configured, it fits a nice big niche. And it actually fits within the concept of what people considered mainframes before. So even though I think mainframe is good, the concept of a big mainframe box is still there, it's being redefined and being used with clustered architectures that can still deliver the levels of reliability and fit the niche that that doesn't fit the HPC realm that you have HPC. And then I think you're going to see more application-specific servers like microclusters and whatnot that can do web services and whatnot at the other end. So that's the answer to that. We've always taken our processors to massively parallel. The first terascale machine that was installed in Sandy in '96 was a P6, and it was a massively parallel system. Many of the top 500s, in fact, the top machine from China 6 months ago was an Intel NVIDIA-based system. So massively parallel was always something we want to push Xeon because using that, they can build good machines with a pretty good price profile. And we don't have to do a lot in terms of being able to scale that machine to work in those, environments. So I don't know if that answers your question, but we've always been working in that path. Now going forward, for the big HPC machines, like I mentioned, those changes, I don't know what it's going to look like yet. So, we got a microphone back there. Sorry. Thanks, Jim.
Since you mentioned exascale, besides Mike, what other areas are you considering exploring, like interconnect, storage, quality of service, stuff like that?
Oh, on exascale?
You mentioned it, so.
Oh, so it's my fault for bringing it up. Hey, Tom, you want to answer? So we're having to go all the way down to the device level. I'll just give you one example, then we need to move on because the time's going away. Sub-threshold logic or near-threshold logic. For years, people have been exploring, can we run transistors below threshold? And threshold, for those who don't know, is the turn-on voltage of the transistor. And if we run the supply voltage at less than the turn-on voltage. That research horribly failed, but it was insightful. It's kind of like what Genevieve said, is if you look at her on the billboard, Intel allows us to be surprised. We were surprised that the devices are actually their most efficient at 20 millivolts above the threshold voltage. So their peak computational efficiency is there. So it's given us insights into how we're going to have to build the next generation systems that aren't going to run at 2 gigahertz. They may have to run at 800 megahertz, but we get peak power performance at that particular point. And that's going to influence how we do memories and everything else. So, there will be application programming changes and things like that, because now we're talking billions of threads, not just, hundreds or tens. So, anyway, thanks. Can you guys ask one of these guys a question up here? I'm running out of breath.
So, we've all heard about the connected world, always on, and many, many sensors providing input for a richer experience. However, you've worked with McAfee on security issues. Do you have any ideas or any work on sensor hijacking?
Yes. The short answer is yes. So we've been doing, last IDF we talked about the sensors in context, and one of the major issues that a lot of people are worried about is the security and privacy. Somebody could write a simple filter driver and spoof your address or your location. I believe we have some technologies in the lab. It's not fully baked, but we are working on it. That will provide some hardware level protection, such that we could encrypt stuff, sensor information in hardware, and directly pass it on to the application.
You know, I'm sorry to interrupt or to add to that. One of my big concerns is anything that has compute, storage, and communication becomes an attack surface. And with the plethora of sensors that are out there, if they're not designed correctly, they're vulnerable to being able to allow somebody to get in and infiltrate the network and do it in a stealth mode. So along that line, it's looking at how you can keep people from being able to get in and actually get control of the sensor itself. And this could be a huge issue going forward.
I have a question about rare metals. They seem to be an important part of the chip production process with so many billions of devices. Are you worried about running out? Are you trying to actively simplify these devices so that you don't need them anymore?
Sounds like mine. In many ways, the rare metal question is a question about cost, really, because ultimately, the cheaper we can make our devices, it tends to be the cheaper materials we want to use. And of course, the devices, the silicon substrate itself, is basically sand, one of the cheapest things around. So the first answer to your question is absolutely, we're trying to move to ever more cheaper materials, which is often moving us off some of the more sophisticated, more expensive materials. Of course, in the case of rare earths, they're an essential component of our high-K gate-back electric, but there aren't very many of them. You know, we're talking, 5-ish layers of atoms. So at that level, we're not really using all that much material to do those sorts of things. One can think of it almost like an efficiency thing, where in those few places where we need those expensive atoms, we put them. But every place else, we tend to try to move toward common, well-known materials that are economical. You see this often in fabrication of interconnects, where we move away from materials like platinum that require armed guards to deliver the targets, and to materials that are much more economical.
You've been waiting so long. Okay, David, and then you're next.
So this is a sort of a storage question. So unfortunately, physics is a cruel mistress, and we can't get speed, capacity, latency, bandwidth all at the same time, let alone cost. So we're going to end up with somewhat specialized storage pools. To what extent do you want software to be able to direct where you place your data? And to what extent do you want the hardware to do it autonomously, perhaps override software? And how do you sort of manage that ball of complexity?
Thank God, storage question.
Those are the real questions.
I feel like the guy that didn't get a dance at the beach or something.
Hey, that's my college career, buddy. Don't worry.
So there's a lot of activity already that's happening on how to best take advantage of the unique attributes of different kinds of storage devices that we have today. So with the SSDs that are already mainstream today, they're 20, 50, 100x faster in terms of random IOPS, but they're not cheap. And just the self-interest of economies already results in people trying to apply that where it's worth it. And so there's already a tremendous amount of effort on tier storage and caching and so on. Even our rapid storage technology driver that comes with the latest chipset has provisions in it now for including both non-volatile storage like an SSD and combining that with the hard drive in order to give you the best attributes of both. So you get the majority of the benefits of an SSD, but at the kind of capacities that you get really inexpensively with hard drives. And of course, that's all done with software today in the driver. So I think that we're already seeing what I think you're implying, a layering of the storage where each of the storage devices is applied where its attributes are the most favorable, and then managing that through storage like the drivers I'm talking about.
Next question.
Yeah. I've got a question for Dr. Kuhn. Can you talk a little bit about lithography? I understand that EUV, whether it's ready economically for running production by 2015, is even up in the air. And I was just wondering, with immersion and double patterning or triple patterning, quadruple patterning, how far can you push conventional lithography before you really need some other things?
That's a fabulous question. Just like the previous question to me, it's all about cost. EUV is not going to end up being a cheap technology. And as you very accurately pointed out, the double patterning, multiple patterning, spacer type patterning strategies are working extraordinarily well. And back when I was in school, people were always putting limitations at 193 nanometers, gee, you could print 193 nanometers. Well, when you move to these patterning technologies that can print something and then put something on the side of it and get rid of the middle and then put something on the side of that, you're able to leverage atomic deposition to make very, very tight geometry structures much better than actual old-fashioned lithography. Plus, if you look at some of the research coming out of MIT and some of these self-assembled structures where you can get the polymers to go nose to tail, nose to tail, nose to tail, and get even finer definition than with spacer patterning, what it means is that available to the patterning community is now a smorgasbord of alternatives. They can do immersion, they can do potentially EUV, they can do double patterning or spacer patterning or directed self-assembly and on and on. And at the end of the day, it's all going to be about cost. We're going to end up doing the cheapest of all these alternatives. I think a very clear message that's come out of the patterning community in the last 5 years is we can do all this. The patterning community can make things as small as you want them to make. It's just going to be which alternative turns out to be the cheapest.
At this point, there's no clear winner.
You relate core microarchitectural performance to system performance or platform performance. When you're going up and down the stack, you have the small devices to the large servers, and in some of these things we are talking about user experience. I was wondering, where does CPU performance sit when it comes to non-CPU performance? What are the trade-offs you think?
Tommy, you've been kind of quiet. Would you like to?
Wow. I'll give that one a try. So when you say CPU performance versus non-CPU performance, I think that covers everything that isn't a CPU. It's not just a graphics question. I think it's all going to come down to how quickly, at the end of the day, that from a user experience, how snappy the platform is. How quickly do you respond to whether it's a stroke on the screen, independent of what else is running. So how quickly can you get from this task to that task, whatever it is. Okay, it's going to be a
So you're saying it's all about storage?
Certainly. Yes. Some of it better be in your cache, too, by the way. No, I think it's really going to come down to things like that. If you take a look at devices like your iPad 2s, your iPhones, it's a snappy experience. The actual amount of hardware underneath that is a lot less than what we have, let's say, on a laptop, if you get that snap. So, all the instant on that we're going after, all of the quick response times is what I think at the end of the day is really going to make the difference. And then performance underneath that, more of that the better. So it's not about no performance, but it's about that experience.
Yeah, but it probably means we actually have to think about developing a new set of metrics for how we measure performance. I mean, historically, Intel's had a very narrow band of thinking about that. And it's not just about how do you measure the performance of each of the component pieces, it's also how do you think about it holistically. What does it take to develop a new set of metrics that let you actually scientifically, rigorously, repeatedly measure snappiness, which seems a bit fluffy, really, Tom. Thinking about how we develop a set of metrics that let you talk about both things like snappiness, but also tactility, notions about, what is instant on wheeling, what's the latency, those things look different across different platforms. We know people tolerate different response times on mobile phones to TVs, for instance. So I think what it's going to take to develop a whole new set of benchmarks here that are about benchmarking not just performance, but experiencing it, kind of an interesting space to operate in.
Oh, and if I'm not mistaken, you and your lab have actually taken on that task, haven't you?
Me and my lab and some of my co-collaborators in SSG, absolutely.
Good, thanks. Next question.
So following up on, so there's been a long history of designing hardware, throwing it over the fence to the software designers to do that. Now, what's going to be the impact moving forward on joint software hardware co-design? I mean, that seems to hold some promise, and I'm wondering what is Intel thinking about that?
I've been working on the problem of it from a kind of a theoretical point of view, and I think you can start with abstract models, and the problem is getting data. So measuring what needs to be measured is a big problem. We've also been working on some tools that allow us to look at things a little differently than VTune does, for example. Instead of saying what's going on in this cache or what's going on in that bus, I'm looking at from the point of view of how well a certain program constructs perform, and then map those down to individual hardware nodes. So I personally think that going at performance, power, and energy all in one fell swoop is possible, and we've even been doing some linear programming models that make some interesting trade-offs in those areas. So that's one answer to the question.
Yeah, and we've actually opened up a couple of research centers, actually 3 of them in Europe, specifically to handle the how will applications and understanding how the applications are going to inform the next generation of hardware development, and down to not only what happens at the core, but in the platform with the memory and the I/O. And can we have a runtime environment that can actually look at the application and tend to reschedule things and take better advantage of the hardware that's available with the application, or vice versa. So, and that's really more of a researchy thing, but we're starting to see some promise, at least with some of the applications with the collaborator that David's been working with a number of things.
There's another extension, which is kind of a complement of what Genevieve is talking about. At the other extreme end, we're looking at working with Sony, for example. We've got like 5 million users of VioCare from whom we're collecting .exe information anonymously with their agreement. And from that, you can get a whole lot better insight on what's going on inside real laptops than you can from Sysmart, MobileMart, very abstracted away benchmark. So measurement, in my view, from supercomputing all the way down to what's going on at desk on laptops is one of the central things that we work on.
I wanted to actually extend that a little bit more, though. I don't know how many people saw David Blythe's presentation about an hour and a half ago. And you look at one of the advantages of integration, sharing in caches, being on the same die. You can start also changing, when you talk about hardware, software, code design, I want to put it in the other domain, just saying, how do people want to write software? How do they want to see the device? And knocking down things like memory copies, because it can be in shared coherent space, leaves open a whole bunch of other opportunities that make it simpler to program, but also more power efficient, because you're not changing data, cacheable, non-cacheable, move it from here, move it across the bus. So there are whole other avenues that are, very, very near term that are happening, and we're evangelizing through the industry.
So one question for Ajay and Knut. Really what we have seen, I've seen some presentations in the last couple of days where we show the 3 major pillars of performance bottleneck around CPU and memory and storage are being addressed, and storage being the one being talked about in some presentations I've gone to as finally being solved. CPUs and memory have accelerated in megahertz of speed, and now storage is going to get better now because of advances in storage. But is it possible that now that we're hearing so much about security, are we actually maybe having another 4th pillar in performance bottleneck that we haven't yet experienced now, where abstract the operating system out, because we all know that has its own performance issues. But from a hardware point of view, security now kind of our new bottleneck that we really don't have much understanding of that.
I can answer, going back to that Sony data, looking at millions of Sony users, sorting their .exes. By the time they spend in all the apps they're running, we're clustering it, and you can find substantial clusters of people whose 35-45% of their time is in one kind of security software or another. It's very surprising.
But anyway, we call it the 3rd pillar internally. So it's a lot closer than the 4th pillar. With a lot of the things, there are, where do you want to do the security check? Where do you want, there's a move to move things more into ring 3 versus what might have been in ring 0. That says it has more ways to be attacked. In the case of what we're doing on graphics, is putting hardware down to validate command streams, make sure things don't go out of bounds. You have ways of putting things in virtualized wrappers and say you can only touch this part of memory, you can't get to the rest of the system. So there are hardware things that you can do about this, and we're paying attention to this all the time. Okay.
On the storage device side itself, I know that some of the future designs that we're working on, that even with the high IOPS rates and the high bandwidth rates that we're talking about for future technologies, that we're approaching it in terms of having all crypto blocks and associated security elements of that be dimensioned to match the bandwidth and the performance of the rest of the system, so that there not be a penalty in terms of performance and latency, whether the security stuff like encryption is enabled or disabled. We want to actually have that be at the same bandwidth as the rest of the pipes, and pipeline is staged with it all to hide the latencies, so that it's not a new bottleneck. Because obviously we want to do some of the things I showed in the class. I don't know if you sat in on it or not, but if you're transferring a gigabyte a second of random IOs, you can't afford to spend a whole lot of time doing anything, let alone waste any time with encryption that isn't at full line rate. And so I'm focusing on full line rate security solutions.
Next. One of the unintended consequences of Moore's law, I think, is that people likely expect their computers to be faster and cheaper every year. As the people responsible for ensuring that is the case, do you ever feel frustrated that there isn't a greater appreciation of just how much hard work has to go into ensuring their computers to be faster and cheaper every year?
Was that a process device question, an architecture question? Emotional question.
Anthropology. So it was a question that required an emotional IQ. So would you like me to explain it for you?
Someday I'm going to write you a review.
I look forward to that day.
No, it's Miss Emotional IQ.
I'm not responsible for Moore's law. That might be Kelin and the rest of you, but it's a fair question.
What the hell was that all about?
Shit, Steve. It was like, how is that different than ever?
Okay.
After that, I get to take a shot at this. I'm going to try to answer that in 2 ways. First, of course, as a technologist, I think we would all love to be able to sell our devices for the amount of emotional effort and work we've put into them, because we're all technologists. But from the other side, one of the things that the steady decreasing cost curve of Moore's law has given is it's spread the technology internationally. It's touched. It could never have touched if it weren't at that price, and if the price didn't keep dropping. So in one sense, as a technologist, you go, oh man, I wish we could sell these things for $1 million a die, because that's the amount of emotional energies in them. On the other side, you say, oh my goodness, by selling them at the prices we do, we touch the world. They go into places you never could have dreamed you've put anything that was that expensive. So that's kind of the schizophrenia we have as technologists.
Did you want to say something?
That was just a great answer.
It was a great answer. One of the things that one of the issues we have to deal with, though, is people are getting used to us making those kinds of things happen. I'll never forget when one of the derivatives of the Willamette processor came out, and the design team, they busted their tail, got it out on time, actually a quarter ahead, and that's what we expect you to do. Now, what's the great thing? So as you do that, the expectations tend to be, yeah, you can do that. Now what's the next great thing you're going to be able to do? So there's a lot of work that goes on, and we appreciate it, but those expectations keep going up. So if she can't deliver as fast as devices with as great power efficiency, it's up to us to be able to figure out architectural ways to compensate for that, because the customers are going to expect it. You got to have a microphone.
Yeah. Can you comment on 450 strategies and approaches of 450 millimeter?
Okay, that sounds like mine, yes. The 450 strategy is probably going to look a good deal like the 300mm strategy. Because at that point, when it becomes economically viable, we will move to 450. I think you're all aware we're building a new fab, D1X in Oregon. The work on it started in February. The fab is going together hand over fist. It's really fabulous watching these things go up. That fab will start out at 300mm and will move to 450 when it becomes economically viable.
So back to transistors and Moore's Law. When does Moore's Law end with semiconductors as we know it, if you disregard price? Where does the physics end? And maybe not a date, maybe size.
It turns out it has a movable answer. It always ends about 2 generations ahead of wherever we are. And I can prove this because about 20 years ago, everyone said Moore's Law would end when Dennard scaling ended, constant field scaling. Well, constant field scaling ended at 130 nanometers, and nobody even noticed because we started putting enhancers in, right? Then, more recently, we heard, well, Moore's Law scaling will end when the planar transistor can't support short channel effects anymore. Well, we just changed that by going to vertical transistors. It turns out that every time we see a major impediment to the physics, and I can name half a dozen of them, the constant law scaling physics, which ended in 130, the silicon dioxide scaling physics, which ended about 65 nanometers, the 193 immersion litho physics, which is ending as we speak, the short channel CMOS physics, which ended at 22 nanometers. Every time we see end to one kind of physics, we just clock in a different kind of physics. The end of Dennard scaling was all the enhancers, strain, and so forth. The end of oxide scaling was the introduction of high-K metal gate and its successors. The end of CMOS was the vertical devices. Litho, we keep generating new ways to pattern after 193 immersion. So every time we see an end to the physics, we put in new physics beyond that.
Okay, I think we only have about 5 minutes left.
5 minutes and 34 seconds, so let's get these things around as quickly as possible.
We're currently using Opal hard drives, and I was wondering if Intel's going to have Opal SSD drives available anytime.
Opal is, of course, for those who may not be familiar with it, is a security and encryption standard for hard drives. And we haven't released or announced an Opal drive yet, but obviously with the security kind of focus that we're talking about, that is something that we're working on, but I'm not in a position to pre-announce a product.
Next.
Is there a notion to introduce quality of service, or you can get a hint from the applications, queue everything up in the processor level, then reorder the workload to save power and data with performance?
David?
Well, I think in the HPC at the high end and servers and so on, quality of service, Intel has worked on it to some extent with Cluster Ready, for example. But Intel is not an operating system company that would start queuing jobs up in a different way. So it's a complicated and open-ended question, but not a lot of work going on inside Intel.
Well, there's work that's going on in terms of the measurement and getting the appropriate heuristics, and then at some point in time we'll be able to take those and apply them with the decision algorithms to decide, okay, how are we going to schedule these? You know, when we look at it, somebody says, hey, this is the kind of power profile I'm looking for. You know, it's going to be at very high power. Do I move it to this particular machine or this one? I'm going to be scheduling different jobs. Can I, you know, because data movement is actually becoming more of a power hog than actually the compute itself. And so how can we schedule it so we do a minimum amount of data movement? So first and foremost is getting the statistics and then putting the decision science around it on what we'll do. Do we have product? No, but we're getting smarter, I would say. It's her job, by the way. Who asked that question? Okay. Oh, Howard gave you a card. Okay.
Do you think the Atom processor will replace the Celeron processor?
Don't look at me.
Ajay. Will replace?
Will it replace the Celeron processor?
I really don't know the answer to this. This is more of a roadmap question. It's nothing to do with technology. It's really a business question. I truly don't know the answer.
When
the cloud environment, multi-tenant security is a big problem. And right now it's being addressed mostly by software. Does Intel have any hardware hooks or security processors that would enable security?
Steve, the cloud.
Thanks. That was as of 2 months ago. We have technologies to be able to container, to set up specific containers. I mean, virtualization with the VMM is able to do that. Are we looking at technologies to be able to do that at a hardware level, at a finer level of granularity? Yes. That means that we're going to have to start bringing along the applications and actually the operating system. So we will be able to have multiple users, multiple containers, and be able to package those around. And if we happen to see that there's an access, or one of the things I was talking about with Peggy yesterday was if we happen to detect that a virus has occurred, we can put a quarantine around that virus and actually set it in some container and put it aside and let the antivirus software at some point later decide how do they want to do it. Do they want to clean it up, or do they want to do something with it but protect the other applications? So, those technologies will help assist in multi-tenancy, but they're certainly not going to be sufficient, if that makes any sense.
Will there be an onboard security process?
I don't know yet. Right now we can do pretty much what we need to do with the general purpose processor with some acceleration technology. If we want to move that and have a dedicated onboard security processor, like we use some of our other things today, we might look at doing something like that, but I don't see that happening because it just becomes security processors can also be integrated for that as well. So, yes. I'm sorry, go ahead. And then I promise I'll bring the mic over to you next.
Okay, I hate being a sexist, but I'm going to ask a question just of the men of the panel, and that's actually because of their specialty.
And that might be?
That is when Moore's Law does stop, if it ever does, and Dr. Kuhn made a very good argument for why it just might never happen. But then, will there be a way to use a fixed transistor budget better in order to continue getting the kind of improvements that we've seen over time?
Well,
well, I'll just answer in a general sense. That we're very much focused on power because at the end of the day, things are getting thinner and lighter. You can't just blow power budgets all over the place. And part of that is to actually get more and more frugal. I think what's happened, if I watch this, I'm older than most people that I work with. We used to draw gates, and now we have people just coding RTO on a keyboard. They don't even know how many gates come out the back end. So I think there are many ways to tighten up these designs and get actually, more performance per transistor, less power per transistor. So I think, just over time, just because, you're putting millions of these things down, we waste things because it's expedient. It's about cost, if you will, cost. So I think there's a different way that can go on here. Now, does that go on forever? I think once you've gotten out all your chisels and go back to those days and, more like a caveman, go back to those technologies, you'll get everything out of it, but, I don't know what happens after that. I think it's a long way to go, though.
So one of the things that could potentially happen is we'll stack in the third dimension. So we won't be asking Kelin to grow 3D transit. Well, she will be doing 3D transit.
Or we already did that.
Yes, there we go. But, having different dye in the third dimension, we actually ran an experiment in the labs several years ago where we took one of our processor cores, partitioned it, and relayed it out so that we could get the capacitance down and actually stack the die on top of each other. In a simulator, we never built it because we couldn't get the power out of the bottom level to keep it from melting. But those kinds of things we'll actually start looking at. We actually have time for one more question. You've been so patient.
I've been curious about the manufacturing process for the Tri-Gate. It just seems so much more complicated than stamping out dies.
Well, you and the rest of the planet, I think, are curious about it.
Do you see today what we put up with?
Give him two. He waited waited all that time.
Yes, you waited all that time.
The shortest answer. Was that the answer?
I will give an advertising snippet for my talk tomorrow.
What time? Okay.
Oh, that was it.
That's okay, Steve.
Unfortunately, we run out of time. We do have a lot more cards, but I think a couple of you have to run to the airport really quickly. So I want to thank everybody for showing up on the panel. I hope